Oh, hello and welcome everyone. This is a talk called Introduction to Hardware Efficiency. So my name is Ivica Bogosavljevic and I'll be talking about this one. And I hope you will have a good time and it will be interesting stuff for you and something that you don't know a lot about. So just short notice, you can ask questions during during the talk. You can type the answer questions in the questions and answer box, and then I'll try to answer them when I finish one part of the talk. I'll try to answer the question so we can have a more live experience. Okay, so as I said, I'm Ivica Bogosavljevic. I'm an application performance engineer or specialist, and my professional focus is making software faster by using better algorithms, by better exploiting the underlying hardware, by better using the standard library, better using programming language and operating system. I also work as a performance consultant. That means that if your company or you have problems with performance of your software, you can use this email address to contact me. And finally, I write a lot about software performance. This is my blog, so feel free to visit. Okay, so let's start. The first thing is related to the question of making software fast. So when we are working in C and C++ world, performance is often an issue because normally the reason why people pick C++ is because they want good performance. If that's not the case, they would pick some language that's easier to develop, like Java, JavaScript, or Python. Now, performance comes in many shapes and sizes and depends on many factors. So in order to get the best performance, you need to consider a lot of things. First thing, which is really important, is software architecture. You need to have software architecture that is designed for performance. So you want to avoid all unnecessary work. You want to use algorithms that have low algorithmic complexity and so on. You want to follow good programming language practices. For example, you want to forward classes by reference and not by value. You also want to have a compiler that is configured good to create efficient machine code. And then finally, one of the important aspects of making software fast is being hardware efficient. So you want to have your software to use the underlying hardware, CPU and memory mostly, but also disk and network in the most efficient way possible. Now, if your goal is striving for peak performance, that the best possible performance, hardware efficiency is definitely something you need to take into account. Okay, so in this talk we talk about, it's called Introduction to Hardware Efficiency, and we talk about better usage of hardware resources. So essentially, when we are investigating hardware resources, there are two major types of bottlenecks. One are called when the bottleneck is if you have your code and the bottleneck is in the CPU itself, so in the chip, we call those called computationally intensive or core bound, and this is limited by the CPU resources. But many other codes are not limited by the CPU resources. They are limited by the amount of data they can transfer from the memory subsystem to the CPU. And we call these programs memory intensive or memory bound. So they're limited by the memory subsystem. A smaller part of the programs which we will not talk about in this talk are those that are disk bound, so where the bottleneck is disk access. For example, if you have a copy command, the bottleneck will be disk access, and also where the programs that are network bound, where the limitation in speed comes from network bottleneck. Okay, so we talk about computationally intensive or core bound and memory intensive or memory bound software, and why we are talking about these two different types of hardware efficiency problems is because optimization strategies for computational intensive are completely different from optimization techniques for memory intensive or memory bound. So I don't see any questions in the question and answer box. I'm moving on. So feel free to ask type in questions, and I'll answer them when the proper chance arises. Now the question is, you might ask yourself, okay, I have this hot loop, or I have this hot code. This is something I'm investigating. Is it memory intensive or is it computational intensive? If you want to figure out that, it's not simple. It's not a simple work, but there are dedicated tools you can use. That the most important dedicated profilers that you can use. Most important are Intel's vTune, which works on Intel, AMD MicroProf, which works on AMD chips. Then you have PMU tools, again for Intel. Perf is a general purpose tool, although a bit limited in functionality, and Liquid. So these are all the tools that you can use to figure out if your loop is memory intensive or computational intensive. Now, if your code has bad numbers in the memory intensive section, that means that data cache miss section is high, so your program is mostly getting data from the memory, which is slow, and so on. Your code will be memory intensive. On the other hand, if you see that there is a high utilization of vectorization units dividers, a large amount of branch misprediction, then your code will probably be computational intensive. Now, the problem with these tools, they have a steep learning curve, so it takes quite some time to master them. And the good thing is that you can determine if your code is computationally intensive or memory intensive just by looking at the code. So this is a good thing. So yes, any questions? Again, I don't see any questions. So moving on. Okay, so the first part of the talk talks about optimizing computationally intensive codes, and the second part talks about optimizing memory intensive code. So let's move on to computationally intensive codes. So the question is, what are the prerequisites to when is a loop computationally intensive? And if you want to make sure that, if you want to check if your loop is computationally intensive, these are the criteria. So first criterion is that the loop is processing simple data types: ints, char, double, float, but these are simple basic data types. Or maybe really small classes, like class with 2 members. If you have a loop that is processing classes with large classes, then that loop will not be computationally intensive. The second prerequisite for computationally intensive is that the data is stored in an array or a vector. So all the data needs to be stored in array or a vector. If you're processing arrays or processing vectors, and they are simple data types, that gives really high chance that the code will be computationally intensive. So if your loop is looking up in std set, std unordered set, std map, so all types of hash maps, or all types of binary trees, n-ary trees, whatever. If your loop is chasing pointers, if it is processing a linked list, in that case, that loop will most likely not be computationally intensive. Okay, and the last criterion, which is also important, is you have a sequential access to values in array. So your loop is processing array, and it is going from 0 to n, or from n to 0, but it is processing elements sequentially: 0, 1, 2, 3, 4, 5, 6, 7, 8. So if you have these three, all of them, simple data types, data stored in array or vector, and sequential access to data, your loop will most likely be computationally intensive, and this means that it will profit from the recommendations I will give later. If at least one of these is not true, then your loop is probably memory intensive. So especially if your loop is processing large classes, if it is looking up data in a binary tree or in a hash map, it will be memory intensive. Now, computationally intensive codes are not that common when you're actually developing, but the CPU executes them a lot. So many image, audio, and video processing algorithms are computationally intensive because the CPU is working on pixels. In machine learning, you have many computationally intensive codes because machine learning uses linear algebra, which internally uses matrices, which are essentially arrays, and it uses it goes through array sequentially, so most of those algorithms are actually computationally intensive. You have also in the telecommunications, many algorithms are computationally intensive, notably fast Fourier transformation, and in scientific computing, you have many computationally intensive codes. Okay, so I have one question here. We do not see your video if it's intentional. I don't know. So I didn't turn off my video. So it says here that the video is running. I hope everything is okay. Okay. The next thing is about fixing memory-intensive codes. So sometimes you have a memory. So a short digression. Sometimes you have memory-intensive code that you can actually convert to become computationally intensive code. So this is possible. This kind of conversion is possible in some cases, although not many. And ideally, it's much better to be computationally intensive than memory intensive. And the reason is quite simple, because CPUs are much faster than memory. So CPU, the amount of data that the CPU can process and the amount of data the memory can deliver to the CPU are just not easy to compare. So it perfect. Ideally, you want to be computationally intensive. So okay, so the question is, what kind of codes can be converted from memory intensive to computationally intensive? The first transformation is called struct of arrays. So if you have classes, instance of a class, many instances, and you store them in an array, it is possible to change from memory intensive to computationally intensive by changing the way the data is represented in memory. So instead of having one array and each instance has a place of its place in the array, you convert, and so if you have a class with many members stored in array, this kind of representation is called array of structs or array of classes. Now, if you change the memory representation by like this, your class has member 1, member 2, member 3, member 4. Now, for each member in your class, you have a dedicated array. So one array holds the member 1, another array holds member 2, another array holds member 3, and so on. So you change the memory layout. The class, as it was earlier, does not exist anymore. So what happens? What happens then is that this kind of memory representation of the class is called struct of arrays, because you have a struct for a class, and inside a class for each member, instead of having just one piece of data, you have an array. For each member, you have an array in the struct, and it's called struct of array. Unfortunately, this conversion needs to be done manually in C and C++. The languages themselves do not provide any facilities to make this easier for you. Okay, here we have an example. We have a class student, which has a std string name and double average mark. And we have a vector of student class. When we convert it to struct of arrays, we have a class students. So please note that this is plural. And inside students, we have a vector that holds names and vector that holds doubles. Now, there is a code that calculates average mark for all students. So for all students, it calculates the average mark. An original code took 194 milliseconds, and this struct of array version took 42 milliseconds. So it was about 4 times faster. Now, the question is why? If you remember correctly, to calculate average marks, you don't care about names. You're just accessing this vector. And this code is computationally intensive. Why? It's processing doubles, simple types. The data is stored in vector. And the third one, we're accessing data sequentially from 0 to n. Okay. So this is one way how to fix memory intensive code, by converting from array of structs or array of classes to class of arrays. The next thing related to fixing memory intensive codes is more about matrices. So if we have our code, the way the matrices are laid out in memory in C is row-wise. So we have row 0, then row 1, then row 2, then row 4, and so on. So we have like This continues. The memory is one-dimensional. The matrices are two-dimensional. So we are putting row after row in memory. Now, if your code is processing data column-wise, it's actually jumping in the memory. So it is accessing the column 0 of row 0, column 0 of row 1, column 0 of row 2, and so on. So this is what happens, is that your program is actually jumping over memory locations for the size of row. Now, this is a problem. As I said, this kind of code is memory bound. It's not computationally bound. But there is this way of fixing it. It's called a loop interchange. So let's explain here. So on the left here, we see a code that does matrix multiplication. So this is a textbook matrix multiplication algorithm. So you see here that C of ij equals C of ij plus A of ik times B of kj. So this is a textbook implementation. If you open your textbooks, you will see there. Now look at these loops. One is over j and the other one is over k. Now let's analyze the access pattern for all three, A, B, and C. So what we're interested in is what happens when k increases by 1. So this is the innermost loop over k, and we want to know what happens when k increases by 1, k plus plus here. So when k increases by 1, the access to C is constant. It doesn't change at all because it's not related. It's independent of k. The access to A, it's same row, just the neighboring memory address. So we are accessing the memory matrix A sequentially. But the matrix B, when k increases by 1, we are accessing in the same column next row. So it translates to these memory jumps. So the CPU is not accessing memory sequentially, it's jumping over memory. It's called the strided memory access. Now, what happens if we interchange, if we exchange the loop over k, this one, and loop over j? So we have written that here. Now let's do analysis again. So we have here the loop over j, which is the innermost loop. Let's see what happens when j increases by 1. When j increases by 1, the access of C is sequential. So because the way the matrix is laid out in memory, we are accessing the neighboring memory addresses. What happens with access to A? Well, the A does not depend on J, so this is a constant access. It's always hitting the same memory address. And finally, what happens to memory access to B? What happens is that when J increases by 1, we are again accessing the next memory element in the matrix. So access to A is constant and access to B and C are sequential. So we're accessing just neighboring memory addresses. And this code does not have this jump, this huge jump. And this code is actually computationally intensive compared to this one, which is memory intensive. And this code actually runs faster several times. So with the matrix size 1,200 times 1,200, the first loop takes 5.8 seconds. The second takes 1.22 seconds. So about 4 times faster. Okay. Questions? I don't see any questions. So let's move on to the next topic. With regards to computationally intensive codes, a really important thing to make to best use the CPU resources, it's called vectorization. So what is vectorization? Many modern CPUs can process more than one piece of data in a single instruction. So what does that mean? The CPU can load 4 doubles in a register that can hold 4 doubles. It can load another 4 doubles in a second register. It can perform two addition, parallel addition, when it is adding 4 doubles from register A and 4 doubles from register B. And it can add them together. And it can store the 4 results to the memory. And this is called vectorization because the code that is executed, it's called vector code. It's often called SIMD, single instruction multiple data, because a single instruction is processing several pieces of data. Now, with regards to vectorization, a really important note is that if the compiler is properly configured and there are good enough prerequisites, the compiler can actually do automatic vectorization for you. It can take your code, which is written like this,
And then in the process of autovectorization, it can use vector instructions. Of course, for this to happen, the compiler must use a high optimization flags like hold 2 or hold 3. It needs to be configured with good architecture flag like MARC native, MARC Cortex A72, MARC Skylake, whatever. So these things need to be configured. So let's investigate what happens. So this is the original loop, really simple loop. A of I equals B of I times plus C of I. And what happens with autovectorization? So we have the same loop, but I, instead of increasing by 1, increases by 4. This happens because the CPU is processing 4 integers by 4 integers. So it works in batches of 4 integers. So it loads B of I to a vector register, bTMP, and it loads C of I to a vector register, ctemp. So we have 2 vector registers holding 4 values for B and 4 values for C. Then it adds together B and C and stores the result to a vector register A of TMP. And finally, it moves back data from the register to the memory from ATMP, so 4 stores, storing 4 integers to the memory. And this is the magic of vectorization. Instead of doing 1 by 1 processing, it does 4 by 4 processing. The number of instructions will be typically 4 times lower, and it will mean faster processing. I'm looking for questions. I don't see any. I hope you're following this. Okay, a few notes about vectorization. So the vectorized code will run typically 2 to 6 times faster. So it really depends. But this is something you can expect 2, 3, 4 times faster. The compilers can auto-vectorize your loops. So if you have a loop, the compiler can actually auto-vectorize your loop when certain conditions are met. If the compiler has auto-vectorized certain part of the code, so if you took a loop and auto-vectorize it, that is a good indication that your code is running at maximum possible speed. Normally, it is really difficult to get beyond that, performance beyond that. Now, if you want to check if your compiler has automatically vectorized loop, you can pass certain compiler flags, like this one for Clang, and the lower one is for GCC. So most compilers support this. So use these flags to get vectorization information if performance of your code is important. Okay. This is about the auto-vectorization. Unfortunately, as you will see later, not all loops are easily auto-vectorized. So what are the prerequisites for auto-vectorization? What the compiler actually requires to auto-vectorize a loop? The first thing, it needs to be with simple data types or really small classes. So simple data types, double, integer, chars, floats, whatever. The reason is if you don't use simple data types, the compiler can auto-vectorize the loop, but it won't do it because it knows that the vectorization doesn't pay off because the problem is memory bound, not computationally bound. The second thing, which is a prerequisite for auto-vectorization, is good memory access pattern. So the loop needs to have the memory access pattern needs to be sequential, so going from 0 to n or from n to 0. If the loop does not access data sequentially, those loops actually are memory bound and vectorization does not pay off, so the compilers do not do it. The third thing is that you need to have independent iteration. So independent iterations is a term coming generally from parallelization, when you want to speed up your code. What does that mean, independent iteration? So data needed inside the current iteration of the loop should be independent on the previous iterations. So that in essence, you can run the loop from 0 to n, or you can run the loop from n to 0. If you can rewrite the indexes of the loops in any way, that means that the loop actually has independent iterations, and that kind of code actually pays off to vectorize. The fourth thing is that the number of iterations can be calculated before the loop starts. So we have a loop which goes from 0 to n, with increment I plus plus. What does that mean is that the n should be fixed constant. It should not change while the loop is running. And also I++, the value of I should be changed in a predictable manner. So it should not change inside the loop body, only in the where the increment changes. So with regards to this, that means that compilers while loops with search while loops. For example, you have a loop that searches end of a string, it searches for 0. That kind of loop typically cannot be vectorized by the compiler because the number of iteration is not known in advance. How many strings do you know? What is the length of the string is the number of iterations, and the compiler does not have that information. So search loops, the compiler will not auto-vectorize them, most of them, although they are possible to vectorize, but not by the compiler. The next thing is that your loop does not have a lot of conditionals. So if you have a loop body and inside you have conditionals, if something, then do something, if something, then do something. What happens is that the CPU, the vector instructions inside the CPU, they do the same operation of the data on the data. So for example, if you have a loop that if the value is positive, do something, and else do something else. If you have such a loop and you want to process it using vector instructions, it becomes difficult. Why? Because there are no instructions that do conditionally, like add if the value is less than 0 and subtract if the value is greater than 0. So conditionals inside of loop make vectorization less efficient, let's say. It's possible to do it, but it's less efficient. And finally, there should be no pointer aliasing. Now, pointer aliasing is, what happens is, imagine like this, your loop is accessing two arrays, array A and array B. Now, if they're independent, then there is no pointer aliasing. But imagine your loop is processing apparently two arrays, but actually just one array with two pointers. So in that case, we say that there is pointer aliasing. Two pointers are pointing to the same block or parts of the same block. They don't necessarily have to point to the same address, but block of memory, they point to the same block of memory. Now, this is a real inhibitor of vectorization, and with this, vectorization does not work. So if your code has pointer aliasing, the compiler will revert to a non-vectorized implementation. Okay, I have a question here, just a second. Will range loop and for each work? So for each are typically not used with doubles. For each, if you have a vector of for each and range loops, in principle, the compiler can vectorize them if all of these prerequisites are satisfied. So there is no reason for that. I probably assume that internally the compiler uses the same representation for range loops, for each loops, and for each loops. But you need to check that. You need to check that with the compiler vectorization report if actually happens. Okay. Moving on. So you are interested in vectorizing a certain loop, but this loop does not vectorize. You see the compiler report, and the compiler report says the loop is not vectorized. Now, what can you do? That's the question. So you're interested that a certain loop gets vectorized. So one of the things that you can do is you can split loop into vectorizable and non-vectorizable part. So if you do this, you split the loop into two loops. The vectorizable part, the compiler will automatically vectorize it, and the non-vectorizable part will be left unvectorized. The compiler will use the scalar instruction. But if the vectorizable part actually does a lot of processing, this can lead to speed improvements. So loop fission is one of the ways to do it. If you have too many conditionals in the loop, you can move loop invariant condition outside of the loop. So what is a loop invariant condition? So imagine a condition, you have a condition inside the loop, but during the whole time, the condition is either true or false. It doesn't change value. It does not depend on the data, and therefore it doesn't change value while the loop is running. So what you can do is technique called loop unswitching. You move the loop invariant condition outside of the loop.
And then you create two versions of the loops. One loop, one where the condition is true, a second one where the condition is false. This is a way to avoid too many conditionals in the loop and make automatic compiler vectorization easier. If you're leaving the loop earlier, you have a for loop with a break statement in it, or you have a while loop, uncountable loop. There is a technique called loop sectioning that will help you enable vectorization. So loop sectioning works. So how does it work? So it works like this. You have a loop. Imagine you have a string and you want to see the length of the string. Now, the problem is the compiler won't vectorize that loop. But what you will do inside a big while loop, you have a small for loop that accesses 4 elements. It reads the 4 elements and check if any of them is 0. And if it's 0, it breaks the while loop. Now, this for loop, really small for loop with 4 iteration can vectorize. If the compiler is smart enough, it can figure out and vectorize it. And this is loop sectioning. So your big loop, you're converting it to smaller sections. You're processing data 4 by 4 by 4 by 4. Okay, so the next thing is if you have a bad memory access pattern. So we said that the prerequisite for automatic compiler vectorization is a good memory access pattern, notably sequential memory access pattern, when you're accessing sequential pieces of data. So you're going an array from 0 to n. Now, if you have an array of classes, you can use the techniques I described earlier, converting them from array of structures to structure of arrays, and this will improve the memory access pattern. And you can also use loop interchange for matrix processing loop. So if you have a bad memory access pattern and loop interchange is possible, you can use that to make the processing, to fix the bad memory access pattern and enable automatic compiler vectorization. And finally, if you have pointer aliasing. Now, there are 2 types of pointer aliasing. One is a true pointer aliasing and one is like false pointer aliasing. A true pointer aliasing happens when you have 2 pointers pointing to the same block of memory. And there is nothing you can do about it. But if you have a false pointer aliasing, the compiler is not sure if the 2 pointers actually alias one another or not. And in that case, it needs to be conservative and it will generate scalar code. Now, if you as a developer know that these 2 pointers do not alias one another, then you can use this restrict keyword to mark 2 pointers as independent of one another. And this will help tell the compiler these 2 pointers are not pointing to the same blocks of memory, and it is safe to automatically vectorize your loop. So if you're working on compiler on vectorization and you're interested to see what's going on, use the compiler optimization report. I gave already flags for that, and it will tell you what you're doing and if you're moving in the right direction. So it will tell you that it cannot vectorize the loop because of possible pointer aliasing or bad memory access pattern or whatever. Just follow the compiler optimization report. Clang has a bit better compiler optimization report. It's more informative compared to the GCCs, but both of them are fine. Okay, I don't have any questions, so I'm moving on to the next slide. So this finishes the talk about optimizing memory-intensive codes. The next is this finishes the talk about optimizing computational intensive codes. The next one is optimizing memory-intensive codes. So we know that the CPUs nowadays are much faster than memory. And that creates a situation when CPUs are actually data starved. So a solution to that is data cache memory. So what is a data cache memory? A data cache memory is a small memory inside the CPU itself, which is really fast but small. Now, if your program is accessing a piece of data which is already inside the data cache, you have a fast access. If your CPU is processing a piece of data which is not in the data cache, it needs to be fetched from the memory to the data cache, then this access will be slow. Now, the problem with the object-oriented paradigm that many programs use memory inefficiently in the sense that they're bringing a lot of data from the memory to the CPU, and this creates that this makes program memory bound, and the techniques that I'll present here will actually help speed improve those codes. Now, you as developers here, if you're way aware of how memory works, then you can use that knowledge to make your code faster and more efficient. Okay, so let's move on. Now, the first question you want to ask yourself is, when do data cache misses typically happen? So when do data cache misses typically happen? So the first thing that happen is when you're dereferencing a pointer for the first time. So imagine you have a class, inside the class you have pointer to some other piece of data, and your dereference is either using operator star or operator arrow. So you're accessing pointer data members. For the first time, this will create data caches. If you're accessing heap allocated objects, so objects allocated using smart pointers, new, delete, malloc free, this creates this will typically result in data cache. If you have a vector of pointers, so you have a vector of pointers, you're running through the vector of pointers and dereferencing a pointer at each access to a pointer, that will create many data cache misses. Also that's called pointer chasing. So imagine you have a linked list. To get the next element, you need to dereference the next pointer. And to get to the next element, you again need to dereference the next pointer. So following linked list in this pointer chasing code will result in data cache misses, typically, not always. If you're also, not only that, if you're accessing a member of array or another data structure in random fashion. So we have here a histogram array, it's called histogram, but we're not accessing it with I. We're accessing it with A of I. Now, if this A of I contains random values, then this access to histogram will be random. So if your code is doing looking up values in a binary, also, if you have an array and you're doing a binary search on the array, then you will typically performing random data accesses. So binary search on array will typically be random memory accesses, and it will result in data cache misses. And every lookup in hash map, which is built around pointers, such as binary tree, hash maps, will result mostly in data cache misses. So std set, std unordered set, std map, std hash map. So next question. So this was the question about when do data cache misses happen. Now we are asking ourselves, when do data cache hits typically happen? So if you're iterating through an array or vector sequentially, the smaller the class, the higher the data cache rate. So if you have small classes, you have higher data cache hit rate. As already said, that the peak performance is achievable only when working with arrays. So memory-bound program won't be running at peak performance because memory is slower than CPU. If you have like a binary tree or you have a hash map, but it's a small hash map and you're doing a lot of lookups, eventually the whole hash map will fill the data caches and access to it will be fast. So the smaller the data structure, the larger the data cache hit rate, more data cache hits you can expect. Huge data structures like huge hash maps, huge trees will typically be much, much slower. The next thing is what is accessed together should be close neighbors in memory. So you have a class and you're declaring members inside the class. Those members that you access together, so in your hot loop, you should declare them next to one another, because this increases the data cache hit rate. And finally, what is accessed one after another should be laid out in memory one after another. So you have linked lists, and linked list consists of nodes. Now, if this is logically node 1 and node 2, ideally, you want to have them next to one another in memory. So node 1, then next is node 2. And this will result in speedups. So a good memory layout. The similar thing applies to binary tree. So the problem with the binary tree is that the binary tree has a left and right pointers. Now you cannot have both of them to be your neighbors, but you can have one of them to be your neighbor. So if you have a binary tree node, if the left one is a neighbor in memory, it will increase the data cache hit rate and actually make your program faster. Now, the question is, how do these recommendations translate to everyday development? So we give some general recommendation how to increase or decrease data cache hit rate. We give some common example of measure performance difference. When you're debugging your code and you're trying to make it faster, you always need to measure. So eventually you can make a lot of assumptions and eventually some of them will turn wrong. So you always need to measure. So we have a first example here is minimum and maximum in array. The question is, we want to find the minimum and maximum in the vector with class size 16 bytes, and the vector is 100 million elements. So if we are looking for minimum and maximum in the same loop, so it takes 207 milliseconds. But if you have one loop for finding minimum and another loop for finding maximum, it takes 368 milliseconds. Now you might ask yourselves, where does this difference come from? The problem is that for the second case, the data set, the whole vector, needs to be brought from the memory to the CPU 2 times. And in this case, it has to be brought only once. So what is the conclusion? Conclusion is that if you need to iterate over your data, iterate only once and do as much work as possible in order to get the good speed improvement. Now in STL you have std min max to find both minimum and maximum. So you don't need to call std min and std max. But this is general, it works for all data. So you want to bring your data from the memory once, do the processing and return it back to the memory and not touch it again. Let's check if I have any questions. Okay, one question. How do you obtain a compiler optimization report? So the compiler optimization report I already give in a few previous slides. Let me just find it. So these are the flags you pass to the compiler. So this will be recorded and you can look it up, and also I'll share this presentation after the talk. Other questions, just a second. We have two more. What architecture was used to collect the timing measurements? What parameters would affect the amount of performance improvement that could be expected on other systems? Now, this was measured on Intel i5, iCore i5 Skylake. It's really a fairly typical system many people have. You can expect the similar speed improvements on almost all systems because all the systems that you have now have the same problem. The CPU is too fast, the memory is too slow. They all have vector units, except from really, really basic embedded system. Most of them have vector units. So this talk applies to most of the system, not all, but let's say 99% of them. Okay, so, okay. Sorry. Okay, moving on. The next example is called linked list memory layout. So we have a linked list with 6 values. And these green squares are actually linked list nodes. So it has 6 values. The question is, this is the physical memory here. So, and these are 3 layouts. The first one is called random layout because the nodes are actually really random in memory. The second one is called the compact memory layout. Why is it called the compact? Because although the nodes are not neighbors, so you see that the nodes are not neighbors, actually they take the least amount of memory possible. They're compact in memory, so they're not dispersed in memory like this one. And finally, we have the perfect memory layout. It's called the perfect because the neighboring linked list node, logical neighbors, are actually physical neighbors in memory. Okay. Now, the question is which layout is best if we are iterating over the linked list? Here we have the numbers. You have 3 linked list sizes, small, medium, and large. Small has 128 doubles, medium has 1 million doubles, and large has 64 million doubles. And we have 3 layouts, random, compact, and perfect. So you see the runtimes. For small, For small linked list, we have all three layouts are pretty much the same in terms of performance. But for medium and large, we see that the perfect layout is much faster than both compact layout and random layout. Same applies for large. You see that the large scales really well. So it is just a little bit slower, but compact and random layout actually scale really, really bad. You see here that from 0.08 seconds going to 8.2 seconds, going to 15 seconds. Now you can control the layout by using a custom memory allocator. And I wrote in this blog post, I wrote about that. So the quest for the fastest linked list. Okay, so the question is, why is perfect memory layout the fastest? So the reason is that inside the CPU, there is a component called data prefetcher. So what is a data prefetcher? So if your program has a predictable memory access pattern, so the CPU can predict, normally it just increases by 1 or increases by n, the CPU can prefetch the data before the data is even needed. And this will result in data being prefetched before needed, and it will result in speed improvement. Now, for if you're accessing arrays or vector, it is trivial to figure out memory access pattern. For CPU, processing arrays and vector is really fast because the memory access pattern is always predictable. So this is the reason why data access is so much faster with the perfect memory layout, because the CPU can prefetch the data before it's even needed. Just a second, let's see if I have any questions. I have two questions. How to build perfect memory list? So to build a perfect memory list, you will need to have a custom allocator. And I wrote that in that blog post I mentioned. So just a second. So in this blog post, you have information how to do it. So it's possible to do, although if you're deleting and doing some changes to the linked list, in that case, it might turn out it's the linked list, the perfect memory layout slowly disintegrates, but you need to check that on your system if it works. How is the compact more compact than the perfect layout? So the compact is not more compact than the perfect layout. Just called the compact because everything's so neatly, tightly packed in memory, but they have the same, with regards to compactness, they're the same. Okay. Okay, moving on to next. Next example is a vector of pointers. So we have a vector of pointers, std vector of base class pointers, and they're pointing to data allocated on the heap. So child class 1, child class 1, child class 2, child class 2, child class 3. So we have this, and we call this optimal layout because the neighboring pointers point to neighboring memory addresses. And the next, we have a non-optimal layout. Non-optimal is that neighboring pointers just point to some random places in memory. So this is a non-optimal layout. So we are measuring how much time does it take to iterate through a vector with 20 million objects, with perfectly optimal layout and perfectly non-optimal layout. When everything is just perfectly non-optimal layout means that the data are just mixed around in memory. So the access is never predictable. A small virtual function takes 384 milliseconds, and with the optimal layout, and about 5 seconds with the non-optimal layout. So it's about 15 to 20 times slower. A large virtual function takes 2.6 seconds for the optimal layout and 16 seconds for the non-optimal layout. So it's about 8 times slower. Now you see that the problem with large virtual memory layout becomes apparent again. So memory layout is really, really important if you want good performance. So how do you fix that? You can fix it by using, instead of vector of pointers, you use vector of values. So why are vector of values faster? So first thing is that all memory is allocated in a single block of memory. So there is only one call to the memory allocator. If you have sequential access to the objects, you have a sequential access to memory addresses. So it's quite predictable. There are no calls to malloc and free. So this is not related to memory, but if you don't have calls to malloc and free, your program will most likely be faster.
You don't have a virtual dispatching mechanism to slow things down. So because you're using vector of values, the compiler can inline small function because the type is known at compile time. But the downside is no polymorphism. If you're interested in speed, you should use vector of values, because the vector of pointers do not guarantee the memory layout. It is also possible to implement array of values with polymorphism. You can find more information about that here. One of the ways to do it is to use STD variant. Instead of vector of pointers, to use STD variant. STD variant increases the data consumption, but on the other hand, you have these neighboring memory addresses and it works faster. Okay, moving on to next. Okay, the next thing we are going to talk about is experiments with class size and member layout. So we want to check what happens if the size grows, if the class size grows. How does that influence software performance? And we see here a class called rectangle. It has two important members. One is called visible, and the other one is called point P1 and P2. It also has these two paddings, pad 1 size and pad 2 size. So these are used, the paddings are used, we increase the size of paddings in order to measure the effects of performance. Now on the right side, we see a function. It's called calculate surface visible. Calculate surface for rectangles that are visible. And what happens here is that we go for, so we get a vector of rectangles, and then we go from 0 to the vector size. If the rectangle is visible, we add its surface to the sum. Now, this code accesses this M visible. It accesses P1 and P2 because it needs that to calculate the surface. Okay. So how does the speed of processing data depends on the size of the class? So we have two functions here. One is called calculate surface visible. It's a blue one. And the second one is called calculate surface all, visible or non-visible. So the first one accesses, calculate surface visible accesses visible, P1 and P2, and calculate surface all accesses only P1 and P2. It doesn't access visible member. So you see here that on the x-axis, we have a size of class in bytes. On the y-axis, we have a runtime. And as the size of class grows, we see that the function, the hot loop takes more and more time to execute. Both calculate size visible and calculate size all, surface visible and calculate surface all. And you see that the speed improvements when we add a lot of data members, a lot of data. For the class of 184 bytes in size, it's almost 4 or 5 times slower. And this applies for both calculate surface visible and calculate surface all. So you see when you add the new data members to a class, the speed of processing gets slower. The next thing is the memory layout. The member layout, data members layout. So the size of the class is same, but we're changing the padding here between the visible and P1 and P2. So what happens? You see here that the class size is 248 bytes. Now, if the function does not access M visible, so this red one, the performance does not change. It's always the same. But if we increase the size of padding, going from 0 to 16 to 32 to 64 bytes, we see the speed degradation. We see that the processing gets slower. So these two, M visible, P1 and P2, are accessed together. But since this but they're not close to one another in memory because of this padding. So when the padding is 0, then the processing is faster. When the padding grows, the processing is slower. And we can see that in numbers actually here in runtimes. It's not that slower, going from 200 to 250 milliseconds. So the question is, why is processing of smaller classes faster? And the reason is that the data is brought to the data from the memory to the CPU is brought in blocks, which are typically 64 bytes in size. When you have a large class, you're bringing data from the memory to the CPU, the data that actually the CPU won't access
they're unused data, and this wastes memory bandwidth. So if you have a hot loop and you're trying to speed it up, if you have a hot loop and the hot loop is processing classes, and you're trying to speed up this hot loop, the way to do it is just to remove all unaccessed members to other classes, and this will make classes smaller and thus faster. Also, the data members that are often accessed together should be declared together in the class definition. So if you have a class, inside you're declaring members, those that you access together, you should declare them one after another. Because this increases the chance that the data members are in the same data cache block. Okay. So let's see if I have any questions. No questions, okay. So the other idea is how to optimize memory bound programs. So if you have random access data structures such as trees and hash map, you can improve them by making a better memory layout. First of the things, you want to make your data as compact as possible. And for that, you have flat data structures. Flat data structures, there is a flat hash set flat binary tree flat map, means that the data are not distributed all around memory. They're in just one compact block of memory. If you're trying to optimize binary trees, you can use a better memory layout. One of them is called 1M, the Boas layout. You can look it up in Google, this layout. I'm not going to talk about it here. Then the other things that you use is, instead of using a binary tree, use an n-ary tree. Because the n-ary tree are shallower, so they have less point of the references when you're looking up. And they're also more cache friendly, because a single node of n-ary tree contains more data than just one piece of data in a binary tree. If you have hash maps, you can switch to more cache-friendly implementation of hash map. One of these implementations is called hash map with open addressing. So this is here. If you need faster hash maps, you should look up hash maps with open addressing. They're more cache-friendly, they work faster. Actually, you have a whole implementation of standard library that are aimed at speed. For example, EA STL. EA is the EA Sports, the game developer. They have their own containers which are faster and more cache friendly. Okay, no questions. So I think we're almost there. The question is when not to optimize. So some of the things related to the memory bound problems work only when the data sets are large enough. We have large hash maps, large linked lists, large binary trees. So if the data set is not large, it doesn't make sense to optimize it, to just wasted effort. So if small data set is a data set that fits the L1 cache, which is typically between 16 kilobytes and 32 kilobytes. Large data set is data set that doesn't fit the last level cache. So in the CPU, there are several caches. In a hierarchy of caches, L1 is the fastest but the smallest, L2 is slower but bigger, and last level cache L3 is the biggest but it's the slowest. So if the data set is larger than the last level cache, for example, a few megabytes, then it actually does make sense to optimize. If you have data structures with a short lifespan, so you create a data structure to use it for a really short time and then you destroy it, they won't benefit from optimization a lot, because creating an optimal memory data structure takes more time and more resources. So if they're really short-lived, it doesn't pay off. So what's the conclusion? For good performance, it is essential. It is really, really important to use available memory bandwidth in the most effective way possible. You should try to avoid random memory access. So if you have prefer vectors whenever possible, if you can, you should try to avoid vector of pointers and prefer vector of values of a vector of STD variant. You want to keep things that you use together close to one another in memory. You want to keep your data set small, so you don't want to have huge data sets. You want to avoid rereading the same data from the memory several times. So you want to avoid transferring the same data several times from the memory.